section shows how to conduct significance tests and compute confidence intervals for the regression slope and Pearson's correlation. Although no assumptions were needed to determine the best fitting straight line, assumptions are made in the calculation of inferential statistics. Naturally, these assumptions refer to the population and not the sample. We will now discuss each of these assumptions. The first assumption is that the relationship between the two variables is linear. If the relationship between x and y is not linear, a different shaped function could fit the data better. The second assumption is homoscedasticity. This means the variance around the regression line is the same for all values of x. A clear violation of this assumption is shown in this figure. Notice that the prediction for students with high school GPAs is very good, whereas the prediction for students with low high school GPAs is not very good. In other words, the points for students with high school GPAs are close to the regression line, whereas the points for students with low high school GPAs are not. The third assumption is that the errors of prediction are normally distributed. This means that the distributions of deviations from the regression line are normally distributed. It does not mean that x or y is normally distributed. Recall that the general formula for a t-test is the calculated statistic minus the hypothesized value of the statistic divided by the estimated standard error of the statistic. As applied here, the statistic is the sample value of the slope, b, and the hypothesized value is 0. There are n-2 degrees of freedom for this test, where n is the number of pairs of scores. Here are the formulas to calculate the estimated standard error of b. The standard error of b is computed by dividing the standard error of the estimate by the square root of the sum of squares x. The sum of squares x is the sum of the squared deviations of x from the mean of x. The method for computing a confidence interval for the population slope is very similar to methods for computing other confidence intervals. For the 95% confidence interval, the lower limit equals b minus t times the standard error of b, whereas the upper limit equals b plus t times the standard error of b. The notation t sub 0.95 is the value of t to use for the 95% confidence interval. The values of t to be used in a confidence interval can be looked up in a table of the t distribution. A small version of a t-table is shown here. The first column, df, stands for degrees of freedom. The second column contains the t-values for 95% confidence intervals, and the third column contains the t-values for 99% confidence intervals. You can also use the inverse t-distribution calculator to find the t-values to use in confidence intervals. The formula for a significance test of Pearson's correlation is shown here. Again, n refers to the number of pairs of scores. This t-value will always be the same as the one obtained in the test of b, since if the slope is 0, the correlation is 0. Thus, if the regression slope is significantly different from 0, then the correlation coefficient is also significantly different from 0. There are several things to keep in mind when computing a confidence interval on ρ, the population value of Pearson's R. The sampling distribution of Pearson's R is skewed. R can be transformed to Fisher's z prime, which is normal. Z prime can be computed easily or found using a computer program. Z prime has a standard error of 1 divided by the square root of n-3. The calculation of the confidence interval involves the following steps. First, convert from R to z prime. Second, find the standard error of z prime. We write this as s sub z prime. Third, compute the confidence interval in terms of z prime using the formula shown. The notation z sub 0.95 means the value of z to be used in a 95% confidence interval. It is equal to 1.96. Finally, you convert the interval in terms of z prime back to Pearson's correlation. You usually do this with a computer program. Here you see an example calculation based on an R of 0.627 and an N of 5. The first step is to convert from R to Z prime. The R of 0.627 is transformed to a Z prime of 0.736. Second, we find the standard error of Z prime. It is equal to 1 divided by the square root of 5 minus 3, which equals 0.707. Third, we compute the confidence interval in terms of Z prime. The Z value for the 95% confidence interval is 1.96. The calculations show that the lower limit of the confidence interval is equal to negative 0.650, and the upper limit is equal to 2.122. Finally, we convert the interval for Z prime back to Pearson's correlation. This can be done with the R to Z prime calculator. We end up with a lower limit of negative 0.57 and an upper limit of 0.97. The interval is so wide because the sample size is so small.